right, we're continuing in Unit 6. This is Section 6.2, Sampling Distributions, Day 2. And so we kind of talked about introducing a sampling distribution, which would be sampling over and over and over and over again. And this is that idea that if we've taken the same sample size from the same population, we start to get a distribution of all those samples, and it starts to reveal things about the population. So it's repeated sampling that gets us a distribution that should be very similar to the population. And so one of the things that we're going to look at today is whether or not we know that we're actually creating something close to the true parameter. So an unbiased estimator is a statistics whose mean of the sampling distribution, so the center of the sampling distribution, is equal to the true value of the value of the parameter. So for instance, if we were to take all possible samples of a chosen size n from the population, calculated a p-hat, so a sample proportion, for each of those samples, then found the average of all of those samples, you would get the actual value of p. So what they're saying is that if I took the average, okay, oh boy, if I took the average of all the p-hats, this would equal p. If I took the average of all my averages, my sample averages, this would equal the true value. And so this is what we would call an unbiased estimator. And so these are two known unbiased estimators. And so as we continue in Unit 7 and on, we will start introducing an idea, and then we'll do it with means and proportions and means. And so that's kind of how we look at each one of these. And so 6.3, we're going to look at all the proportions, and then 6.4, we'll start looking at means. And so this is the idea that these are unbiased. So if I take a sample proportion and I take another one and another one and another one and another one, overall, they will start to, on average, give me the true proportion that I was looking for that might have been unknown. And so if we look at our first example, it says the histogram above shows the intervals in minutes between the eruptions of Old Faithful Geyser for all 220 eruptions during a particular month. Okay, so I went to, this is in Yellowstone National Park, and so Old Faithful is this geyser, and they literally named it Old Faithful because it's pretty predictable on when it's going to erupt and how high it erupts, which is kind of a crazy thing. And so you just sit here waiting for this phenomenon to happen. And so they have like benches all the way around the geyser, and they're just like waiting for you, or waiting for the geyser to go off, and you have a huge group of people. But surrounded by this geyser are all these little mini geysers that some go off, some like are bigger than Old Faithful. But it's this idea that in 1 month there were 222 eruptions. Okay, so how long did it take from eruption to eruption? Some people had to wait 40 minutes between eruptions, but not really any less than that. So if you get there and it's just gone off, you have to wait at least 40 minutes. Some people had to wait almost 100 minutes in order to see the eruption again. And so this is the interval of time in between those eruptions where it's just going straight up. And so again, this is taking on some distribution here. It's not approximately normal. It's kind of got two peaks going on here. And it says this is our population idea because this was all of them. All right, so then when we looked at this one, for this population, the median, okay, so we know the median here is 75 minutes. So 50% of the time you have to wait less than 75 minutes, 50% of the time you have to wait more than 75 minutes. We then used Fathom software, and Fathom is just a computer software program that takes 500 SRSs of size 10 from this population. So that would be if I went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I took 10 of these observations, and I'm going to find the sample median of that. Okay, so if I took 10 of these, found the median, and then plotted it here. All right, so this is 500 of doing that. So I would have to try this again. So I would take away all my dots. There's one sample, and then I would do it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Find the median, and then I would do it again. And I don't want to do this by hand, so that's why we had the software do this 500 times. And so inside of this, there are 500 medians inside of this distribution. And so when we look at this one, it says we have 500 values of the sample median that are displayed in this histogram here. The average of these 500 values, so the average of all the medians, is equal to 73.5. So the question is the sample median an unbiased estimator of the population mean? And so what we would think of is the average of all those medians equal to the true median? This is our question. When we think unbiased estimator, we want these two things to be equal. So when I look at the population, I have 75. When I look at the average of all the medians we took, I get 73.5. That is not equal. So we would say no, because the average of the sampling distribution because the average of the sampling distribution of medians does not equal the population median. So this would not be an unbiased estimator, meaning there's some bias in medians that is keeping it from being the exact same as that 75. All right. So suppose we had taken samples of size 20 instead of size 10. So now we're going to go back to here, and instead of doing 10, we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and then find the median. Okay? Would the spread of the sampling distribution be larger, smaller, or about the same? And so this is where we've taken our sample size of 10 and increased it to 20. So anytime you increase the sample size, you decrease the variation. So the spread will be smaller. Anytime you want more reliable, more consistent results, increase your sample size. These two things are inversely related. So as you increase your sample size, you're going to decrease the variation. And this is a good thing on both of those things. Increasing your sample size gets you more replication. Decreasing your variation is more consistent, more precise results. So if we looked at the sampling distribution, okay, this is our sampling distribution here, because this is where we sampled 500 times a median. So this is our sampling distribution. So how would we describe this? Okay, anytime we have describe, we want to be thinking SOX. They've specified the shape. So we would say this is a skewed left. Let me double check that. Yep, I think that looks skewed left distribution. There were more medians on the upper end than there were on the smaller end there. All right. Our second example says the Fathom screenshot. So again, this is just a computer program that has done the sampling for us because we don't want to do it by hand. Okay, the Fathom screenshot below shows the results of taking 500 samples of 10 temperature readings from a population distribution that is normal, centered at 50 with a standard deviation of 3. So they're telling us, okay, here's our population. The population is approximately normal, centered at 50 with a standard deviation of 53. Okay, so they're telling us this is what the population reads. Okay, what they did was they took 500 samples of 10 temperatures. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then they recorded the sample minimum each time. Okay, so here would be my minimum, and then they record it. So maybe about 45. And then they would do this again. So then they would take it, and they would do this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And there's my minimum. Now it's about 43, 43 and a half, and they would record it. And they did this 500 times. That's why we have our computer program that does that for us. And so typically we won't be asked to do the sampling distribution. They will say, here's the results of doing it. And so 500 samples, we start to see kind of this distribution that's being taken on. So if I looked at one particular dot, so any dot inside of here, whether it was this one, or this one, or this one, or this one, or any one inside of here, the lowest one, the highest one, what would one individual dot represent? And so this would be one dot is going to be the minimum temperature from a sample of 10 temperatures. So when they look at this particular dot here, that means when we took their 10 from the population over here, there was one where it was at about 43. Okay, that could have been this sample. And then they did it again, 500 times. And so again, we looked at this just doing it once, doing it twice and recording it. There's 500 dots inside of here where each one of those represents 10 temperature readings and the minimum of those 10 temperature readings. So when we look at this, we would say, describe the approximate sampling distribution. Okay, so here's the sampling distribution. And so I might say this is starting to look approximately normal, but maybe slightly skewed left. Okay, slightly skewed left. There doesn't appear to be any outliers. We definitely have a minimum up here and a higher one up here. So I would say there's no outliers, so no unusual readings on the temperature. Centered, okay, so where is this centered? Probably around 45, 46. So centered around 45 degrees and spread of about 10 degrees. We go from about 50 down to about 40. So maybe about 12 degrees actually there, looking at the max and the min. So again, this is looking at this distribution. And so the follow-up question here says, suppose that the minimum of an actual sample is 40 degrees. Okay, so when it says actual, we have this idea where we are simulating it. I almost put pretend. But we're doing a little bit more than just pretending. We're simulating this scenario. And so when we have simulated this, this is what we would get. So if you are actually measuring and taking 10 here, so you're actually measuring those 10 degree or 10 temperature measurements and finding the minimum. So suppose it was actually 40 degrees. All right, so at 40 degrees, we would be about here. Okay, all of these are the simulation. So this is saying the Fathom screenshot below shows the results of taking 500 samples of 10 temperature readings from a population distribution that's here. So this is what the thermostat company has claimed is the population, that here's where our thermostat will keep in consistency. And so when we look at this, it says, suppose that the minimum of an actual sample is 40 degrees. So maybe you start to suspect maybe what they've claimed is incorrect. When we look at this actual data, does this one happen very often? Okay, ours is expected to be around 45. There are no outliers. This is pretty unusual here. So when we look at a minimum of 40 degrees, what that is telling us, we would say this is unusual. Okay, this minimum is unusual if the thermostat is working properly. So if we had here our actual, there's only one that's even less than this. And so if we simulate this, this would be the idea of, the company claims your battery on your car should last 3 years. Okay, so they've made this idea of a distribution where they've taken so many batteries and said, okay, this is on average how long they last. If yours dies after 1 year, okay, is that typical, kind of in the middle there? Or is it actually unusual for what they've claimed is going to be true for the average life of the battery? That's what we're doing here with the thermostat. When we have this claim that's been made by the company and we actually measure something that's 40 degrees, this is pretty unusual. It's not an outlier, but it's not happening very often. And so I would say that I have reason to start to doubt the claim that my thermostat's working properly because of how unusual that observation is from what I was expecting. I was expecting an average around, a minimum around 45 degrees, and we got a minimum that was 40. That difference is pretty significant based on what we sampled here or simulated here. All right, so when we're looking at sampling distributions, we want to kind of think about, is it approaching what we would expect? Is it far away from what we expect? And does that give me evidence against a claim or for a claim? And so let me know if you have any questions, and I hope you have a good day.